Greetings, everybody. Welcome back to Learning as a Hobby. I want to do start a new series here. I know I got a lot going on, but this is what I'm motivated to do right now. So this is what I'm going to do for the moment. Um, I want to go through Terry Tao's 2-volume book on analysis. He has analysis 1 and analysis 2. I don't know if I'll go through the entire thing, but I'll go until I get bored. Or I don't know, other things come up, but I want to at least go through chapter 1 in the next couple of weeks. So I think what I'll start with is um, I'll read through the preface in the first volume here, and then I'll go through my lecture notes for sections 2.1 and 2.2, because chapter 1 is basically motivation for why he wrote the book the way that he wrote it. So let me go to his preface first, and then I'm actually going to skip going through chapter 1, because you should read it yourself. It's kind of a longish chapter where there's no exercises and things like that. It's just a bunch of like I said, motivation for why he's doing things the way he's doing them, but it is worth the read. So I recommend reading that. But let me go to the preface. All right, so here we go at the beginning of the preface. This is from Terry Tao himself, Terrence Tao. This text originated from the lecture notes I gave teaching the honors undergraduate level real analysis sequence at the University of California, Los Angeles in 2003. Among the undergraduates here, real analysis was viewed as being one of the most difficult courses to learn, not only because of the abstract concepts being introduced for the first time, for example, topology, limits, measurability, etc., but also because of the level of rigor and proof demanded of the course. Because of this perception of difficulty, one was often faced with the difficult choice of either reducing the level of rigor in the course in order to make it easier, or to maintain strict standards and face the prospect of many undergraduates, even many of the bright and enthusiastic ones, struggling with the course material. Faced with this dilemma, I tried a somewhat unusual approach to the subject. Typically, an introductory sequence in real analysis assumes that the students are already familiar with the real numbers, with mathematical induction, with elementary calculus, and with the basics of set theory, and then quickly launches into the heart of the subject, for instance, the concept of a limit. Normally, students entering this sequence do indeed have a fair bit of exposure to these prerequisite topics, though in most cases, the material is not covered in a thorough manner. For instance, very few students were able to actually define a real number, or even an integer, properly, even though they could visualize these numbers intuitively and manipulate them algebraically. This seemed to me to be a missed opportunity. Real analysis is one of the first subjects, together with linear algebra and abstract algebra, that a student encounters in which one truly has to grapple with the subtleties of a truly rigorous mathematical proof. As such, the course offered an excellent chance to go back to the foundations of mathematics, and in particular, the opportunity to do a proper and thorough construction of the real numbers. Thus, this course was structured as follows. In the first week, I described some well-known quote-unquote paradoxes in analysis, in which standard laws of the subject, for example, interchange of limits and sums, or sums and integrals, were applied in a non-rigorous way to give nonsensical results, such as 0 equals 1. This is what he talks about in chapter 1, so that's the chapter I'm going to skip. But again, you should read it, just because it's interesting to see these problems that can crop up if you don't have a rigorous understanding of what you're doing. Um, so continuing, this motivated the need to go back to the very beginning of the subject, even to the very definition of the natural numbers, and check all the foundations from scratch. For instance, one of the first homework assignments was to check, using only the piano axioms, that addition was associative for natural numbers. For example, that a plus b in parentheses plus c equals a plus and then b plus c in parentheses. For all natural numbers ABC, see exercise 221. That's one of the exercise sets that we'll get to in the next video. Thus, even in the first week, the students had to write rigorous proofs using mathematical induction. After we had derived all the basic properties of the natural numbers, we then moved on to the integers, initially defined as formal differences of natural numbers. Once the students had verified all the basic properties of the integers, we moved on to the rationals, initially defined as formal quotients of integers, and then from there, we moved on via formal limits of Cauchy sequences to the reals. Around the same time, we covered the basics of set theory, for instance, demonstrating the uncountability of the reals. Only then, after about 10 lectures, did we begin what one normally considers the heart of undergraduate real analysis: limits, continuity, differentiability, and so forth. Let me just pause here for a second. His construction follows pretty closely. It's sort of like I talked about the book Foundations of Analysis by Landau, which I have on my bookshelf up here. It follows sort of the same type of construction as Landau. I think Landau does Dedekind cuts though, and one of the things I think I'd like to do is go through Landau again while I'm reading this, and just noting the differences between the developments. So anyway, continuing here with the preface. The response to this format was quite interesting. In the first few weeks, the students found the material very easy on a conceptual level, as we were dealing only with the basic properties of the standard number systems, but on an intellectual level, it was very challenging, as one was analyzing these number systems from a foundational viewpoint. In order to rigorously derive the more advanced facts about these number systems from the more primitive ones. One student told me how difficult it was to explain to his friends in the non-honors real analysis sequence, A, why he was still learning how to show why all rational numbers are either positive, negative, or zero, which is exercise 424, while the non-honors sequence is already distinguishing absolutely convergent and convergent series. And B, why, despite this, he thought his homework was significantly harder than that of his friends. Another student commented to me quite wryly that while she could obviously see why one could always divide a natural number n into a positive integer q to give a quotient a and a remainder r less than q, exercise 235, she still had, to her frustration, much difficulty in writing down a proof of this fact. I told her later in the course she would have to prove statements for which it would not be as obvious to see that the statements were true. She did not seem to be particularly consoled by this. Nevertheless, these students greatly enjoyed the homework, as when they did persevere and obtain a rigorous proof of an intuitive fact, it solidified the link in their minds between the abstract manipulations of formal mathematics and their informal intuition of mathematics and of the real world, often in a very satisfying way. By the time they were assigned the task of giving the infamous epsilon and delta proofs in real analysis, they had already had so much experience with formalizing intuition and in discerning the subtleties of mathematical logic, such as the distinction between the for all quantifier and the there exists quantifier, that the transition to these proofs was fairly smooth, and we were able to cover material both thoroughly and rapidly. By the 10th week, we had caught up with the non-honors class, and the students were verifying the change of variables formula for Riemann-Stieltjes integrals, and showing that piecewise continuous functions were Riemann integrable. By the conclusion of the sequence in the 20th week, we had covered, both in lecture and in homework, the convergence theory of Taylor and Fourier series, the inverse and implicit function theorem for continuously differentiable functions of several variables, and established the dominated convergence theorem for the Lebesgue integral. In order to cover this much material, many of the key foundational results were left to the students to prove as homework. Indeed, this was an essential aspect of the course, as it ensured the students truly appreciated the concepts as they were being introduced. This format has been retained in this text. The majority of exercises consist of proving lemmas, propositions, and theorems in the main text. Indeed, I would strongly recommend that one do as many of these exercises as possible, and this includes those exercises proving quote unquote obvious statements. If one wishes to use this text to learn real analysis, this is not a subject whose subtleties are easily appreciated just from passive reading. Most of the chapter sections have a number of exercises which are listed at the end of the section. To the expert mathematician, the pace of this book may seem somewhat slow, especially in the early chapters, as there is a heavy emphasis on rigor, except for those discussions explicitly marked quote unquote informal, and justifying many steps that would ordinarily be quickly passed over as being self evident. The first few chapters develop in painful detail many of the quote unquote obvious properties of the standard number systems. For For instance, that the sum of two positive real numbers is again positive, exercise 5.4.1, or that given any two distinct real numbers, one can find a rational number between them, exercise 5.4.5. In these foundational chapters, there is also an emphasis on non-circularity, not using later, more advanced results to prove earlier, more primitive ones. In particular, the usual laws of algebra are not used until they are derived, excuse me, and they have to be derived separately for the natural numbers, integers, rationals, and reals. The reason for this is that it allows the students to learn the art of abstract reasoning, deducing true facts from a limited set of assumptions in the friendly and intuitive setting of number systems. The payoff for this practice comes later when one has to utilize the same type of reasoning techniques to grapple with more advanced concepts, for example, the Lebesgue integral. The text here evolved from my lecture notes on the subject and thus is very much oriented towards a pedagogical perspective. Much of the key material is contained inside exercises, and in many cases, I've chosen to give a lengthy and tedious but instructive proof instead of a slick abstract proof. In more advanced textbooks, the student will see shorter and more conceptually coherent treatments of this material, and with more emphasis on intuition than on rigor. However, I feel it is important to know how to do analysis rigorously and quote by hand first in order to truly appreciate the more modern intuitive abstract approach to analysis that one uses at the graduate level and beyond. The exposition in this book heavily emphasizes rigor and formalism. However, this does not necessarily mean that the lectures based on the book have to proceed in the same way. Indeed, in my own teaching, I have used the lecture time to present the intuition behind the concepts, drawing many informal pictures and giving examples, thus providing a complementary viewpoint to the formal presentation in the text. The exercises assigned as homework provide an essential bridge between the two, requiring the student to combine both intuition and formal understanding together in order to locate correct proofs for a problem. This I found to be the most difficult task for the students, as it required the subject to be genuinely learned rather than merely memorized or vaguely absorbed. Nevertheless, the feedback I received from the students was that the homework, while very demanding for this reason, was also very rewarding, as it allowed them to connect the rather abstract manipulations of formal mathematics with their innate intuition on such basic concepts as numbers, sets, and functions. Of course, the aid of a good teaching assistant is invaluable in achieving this connection. With regard to examinations for this course based on the text, I would recommend either an open book, notes examination with problems similar to the exercises given in the text, but perhaps shorter with no unusual trickery involved, or else a take-home examination that involves problems comparable to the more intricate exercises in the text. The subject matter is too vast to force the student to memorize the definitions and theorems, so I would not recommend a closed book examination or an examination based on regurgitating extracts from the book. Indeed, in my own examinations, I give a supplemental sheet listing the key definitions and theorems which were relevant to the examination problems. Making the examinations similar to the homework assigned in the course will also help motivate the students to work through the and understand the homework problems as thoroughly as possible, as opposed to, say, using flashcards or other such devices to memorize material, which is good preparation not only for examinations, but for doing mathematics in general. Some of the material in this book is somewhat peripheral to the main theme and may be omitted for reasons of time constraints. For instance, as set theory is not as fundamental to analysis, as are the number systems. The chapters on set theory, chapters 3 and 8, can be covered more quickly and with substantially less rigor, or be given as reading assignments. The appendices on logic and the decimal system are intended as optional or supplemental reading and would probably not be covered in the main course lectures. The appendix on logic is particularly suitable for reading concurrently with the first few chapters. Also, chapter 5 on Fourier series is not needed elsewhere in the text and can be omitted. For reasons of length, this textbook has been split into 2 volumes. The first volume is slightly longer, but can be covered in about 30 lectures if the peripheral material is omitted or abridged. The second volume refers at times to the first, but can also be taught to students who have had a first course in analysis from other sources. It also takes about 30 lectures to cover. And then he gives, his thanks for the people that helped him write the book and so on. Um, so like I said, I'm going to actually skip chapter 1. And I think if you have no experience with proofs, it might be uh, worth your while to read through the appendices on logic and proofs, because he gives a background on like proof techniques and the the logic stuff that you need in order to be able to do proofs. Um, I'm going to skip that here, or I think what I might actually do, just to, if you'll, if you'll pardon me, promote my Patreon channel, I might do the appendices for this book on the Patreon page. So if you want to see that, you can go over there. But like I said, I'm gonna skip chapter 1 because it's on motivation for, the way he's developing the subject. But I do recommend you read it. However, I'm gonna start in chapter 2. And I've already gone through section 2.2, or I've written up my notes. I've read the entire chapter 1 and chapter 2 already, but I haven't done the exercises yet. I'll do that in the next video. But we're going to go through my summary notes for section 2.1 and 2.2 in this video. So let me bring them up and we'll go over them. And I'll remind you also that when I go through my summary notes, they are just basically like a skeleton of the chapter. You should definitely read the chapter in the book yourself, because there's a lot more of informal conversation and stuff in the chapter itself, by Terry Tao. It reminds me a bit of the way that Spivak wrote his calculus book, in that you have your formal definitions and theorems and so on and proofs, but in between he has some more informal conversational material that motivates the theorems and gives you some intuition towards what you're doing. So it's worth reading the chapter on your own. So this is like the bare bones. This is just the skeleton of the chapter without any of the flavor of Terry Tao in it. So I would definitely recommend picking up the book and reading it yourself. But let's go through the definitions and the theorems and stuff in these sections. So I'll start in section 2.1. What he does in chapter 2 is he develops the set of natural numbers using the axiom system developed by the mathematician Giovanni Piano, I think his name was. So we'll look at some of the axioms in this section. And I believe there are axioms in the section 2.3 that we haven't talked about yet. But let's go through 2.1 and 2.2 today. All right, so starting with the informal definition of the natural numbers, which is definition 2.1.1. This is the way he labels things in the book. You have the chapter number here, you have the section number here, and then this is the numbering of the definitions and propositions and et cetera, et cetera. So this is the first definition, right? And he says this is informal because we haven't actually defined the natural numbers formally yet. All right, so the informal definition is: a natural number is any element of the set containing the numbers 0, 1, 2, 3, 4, ... which means, it goes on forever. So all of the counting numbers along with 0. Now, before I read the rest of this definition, this is not necessarily a standard definition for the natural numbers. For example, some books omit 0 from the set of natural numbers, while some include it. In this book, Tao defines the natural numbers to include 0. So just be aware of that. If you read another book, the natural numbers might be defined slightly differently in that it might not contain the number 0, but here in Tao's book it does. All right. So here, any natural number is an element of the set 0, 1, 2, 3, 4, 5, 6, 7, etc., which is the set of all natural numbers created by starting with 0 and then counting forward indefinitely. We can call n the set of natural numbers. Now here, this is informal because we haven't defined what set means, and we haven't defined what an element of a set is, and so on. So that's why he's calling this informal. We don't really know necessarily. I mean, we kind of do, but we don't know the formal definitions of these things. So that's what we're heading towards developing. All right. And then here he just gives that note that I mentioned. Some books don't define the natural numbers in a slightly different way. So for us, if n, certain books define the natural numbers as the counting numbers without 0, but in Tao's book, he'll denote that set as z with a superscript plus, which means the positive integers. All right. Just another note, the increment operation or successor operation in this book is denoted by n plus plus. Again, this is not standard notation. This notation comes from computer science, which he talks about in the book. In other math books, sometimes I would say usually, the successor function is denoted like this, S of n. But he doesn't use that notation in this book. He uses this one instead. So just, be aware of that. When you see this symbol here, this means the successor of the natural number n. Right, another note, we will use the notation x with a colon and an equal sign y to mean x is defined equal to y. This is computer science notation. So if you have taken classes in computer science, this is usually the way you define something. So he uses that notation in the book to define something in terms of something else. All right, so we get to our first couple of axioms here. So here's axiom 2.1. And the first axiom is 0 is a natural number. Axiom 2.2 is if n is a natural number, then the successor of n is also a natural number, right? So axioms are statements that do not need to be proved. They're assumed to be true from the start. So that you try for axioms to come up with statements that are so obvious that no one would really argue with them. Now, of course, you could find somebody to argue with anything, but at least, these statements here, like 0 is a natural number, is sort of, I don't know, what's the word, like low level enough that most people would agree that that's okay, okay to assume, if that makes sense. Okay, so these are our first two axioms. We also have a definition here. We define 1 to be the number, the successor of 0. 2 is the successor of 0. 3 is the successor of the successor of the successor of 0, etc., like that. And by definition, you would mean 1 is defined to be the successor of 0, right, and so on, like that. Right, so this symbol means this successor, and so on. Okay, proposition for first proposition in the chapter, proposition 2.1.4. 3 is a natural number, so we can prove this now just with what we've established so far. So here's the proof. So 0 is a natural number by axiom 2.1. Oh, I should say also, before I go through this, my proofs in this in my summaries, you may find are slightly different from Terry Tao's proofs, and that's because when I go through a textbook, and you should try this too, I try to prove the statements myself before I look at the author's solution. It gives you a better insight into what's going on, and you'll understand the author's proof better if you do it that way. So some of my proofs are slightly different than Tao's proofs, but they are, they're logically sound. So some of them are practically the same as Terry Tao's proofs because there's such simple proofs that it's just obvious to do it that way. But anyway, just be aware of that. Some of the ways that I prove the statements here are slightly different than the way that Tao does it. Okay, so going back to the proof. 0 is a natural number by axiom 2.1. Then if you look at the successor of 1, it's a natural number by axiom 2.2. Sorry, not 2.2. Was it 2.1.2? I think it should be, right? Oh no, he labels the axioms differently. So these are the axioms for chapter 2. All right, so by axiom 2.2, and the successor of 1 is equal to 2, which is also a natural number by axiom 2.2. Finally, 3 is the successor of 2 by definition, and it's a natural number by axiom 2.2. So if you have a natural number, its successor is always a natural number, and that shows that 3 is a natural number. All right. The little box here, of course, if you haven't seen any of my other videos, the little box here means the proof is over. Okay, so to prevent what he calls wraparound, we introduce another axiom. By wraparound, he means, sort of like modular arithmetic. For just to give an example of a number system that wraps around, if you look at an analog clock with the hand that goes around, right, and labeled 1 all the way to 12. If you look at an analog clock, once you go past 12, you wrap back around again to the number 1. So for example, 13 in clock arithmetic is the same thing as the number 1. So to prevent things like that happening in our natural number system, we need axiom 2.3. Right? So 0 is not the successor of any natural number. Okay, and we have another proposition here that we can prove. Proposition 2.1.6 says that 4 is not equal to 0, and now we have enough machinery built up that we can prove this. So here we go. By axiom 2.1 and 2.2, 3 is a natural number, since 3 is the successor of the successor of the successor of 0. Also, 4 is the successor of 3, and by axiom 2.3, which is the one we just looked at, 4 is, which is the successor of 3, cannot be 0 because 0 is not the successor of any natural number. So 4 is distinct from 0. In other words, you don't wrap around. 4 never wraps around to 0. Right. Next axiom, which is 2.4. Different natural numbers must have different successors. In other words, if n and m are natural numbers, then the successor of n is not equal to the successor of m. Similarly, another way of saying the same thing is if the successor of n is equal to the successor of m, then n has to be equal to m. Right. Here's another proposition. So this is proposition 2.1.8, which says 6 is not equal to 2. Right, and now we have enough machinery to do this. So here's the proof. Assume that 6 is equal to 2. So we're going to do this by contradiction. Then 6 is the successor of 5, equals. So here we assume that this was true. 2 is the successor of 1. So that would mean that the successor of 5 is equal to the successor of 1, which implies that 5 is equal to 1. Which implies the successor of 4 is equal to the successor of 0, which implies that 4 equals 0, all by axiom 2.4. However, 4 is equals 0 contradicts axiom 2.3, therefore 6 is not equal to 2. Right. Again, that box just means the proof is done. Axiom 2.5, he says, should really be called an axiom schema, because what it does is give a recipe for proving a statement for or a proposition for an infinite number of things. But let's read it out. This is the principle of mathematical induction, which is an important foundational, since it's an axiom, foundational thing for the natural numbers. So let P of n be any property pertaining to a natural number n. He does mention that technically this is, we haven't talked about what properties are, and these like statements, these logical statements, what something like this even means. He goes through that stuff in the appendix, but we'll just continue as if we we kind of know what it means so far. Like I said, I'll be doing the appendices in the Patreon page, so you can look at that if you want. So let excuse me. Let P of n be any property pertaining to a natural number n. Suppose that P of 0 is true, and suppose that whenever P of n is true, P of the successor of n is true, then P of n is true for every natural number n. We've actually already met the principle of mathematical induction in Spivak in a previous chapter a while back, if you remember. I think it might have been chapter 2 that we did stuff with the principle of mathematical induction. But here it is again, as one of the piano axioms. So here again, just repeating what I said a second ago, technically axiom 2.5 should be called an axiom schema, since it gives a template for producing an infinite number of axioms rather than being a single axiom itself. Since it refers to properties as well as variables, it is different in nature than the other 4 axioms. Okay, proposition template 2.1.11. So here he's giving the template for doing basically for doing a proof of a proposition using the principle of mathematical induction. Again, we've done a bunch of these already in Spivak, so hopefully if you've seen those videos, you have some experience with what a proof by mathematical induction looks like, but this is the sort of like the outline. All right, so P of n is true for every natural number n. Here's the proof template. Show that P of 0 is true, and then second step is show that P of the successor of n is true under the assumption that P of n is true. Just to give some vocabulary, this is usually called the base step, and this is usually called the inductive step. Okay, here's a note. Axioms 2.1 to 2.5 are called the piano axioms. Here's a informal assumption, which he calls 2.6. There exists a natural number system n whose elements we will call natural numbers, for which axioms 2.1 to 2.5 are true. We haven't shown this, but he's saying here this is an assumption so far. So we're assuming that such a number system exists, right? And here's a note. This assumption will be made more precise after the notation for sets and functions are laid down in chapter 3. So that's something we'll do in a little while. Not in this video, obviously, but I mean, like, in later videos. Proposition 2.1.16. This is for recursive definitions, which we have the tools now to prove. So suppose for each natural number n, we have some function f sub n from the natural numbers to the natural numbers. Let C be a natural number, then we can assign a unique natural number an to each natural number n such that a0 is equal to C and the a of the successor of n is equal to fn an for each natural number n. Right, here's the proof. And I think this is the last thing in section 2.1, but we're going to go over 2.2 also in this video. So here's the proof of the recursive definition. Sorry, it's not a definition, it's a proposition. You don't prove definitions. So we're assuming that you can do this for natural numbers is what is being asserted. Okay, so assume for each natural number n, there exists a function f sub n from n to n, and let C be a natural number. We proceed by induction. So step 1 is the base case, so define a0 to be equal to C. Then by axiom 2.3, 0 is not the successor of n for any natural number. Therefore, a0 will never be redefined by any of the successive terms in the sequence. All right, so you get uniqueness. Step 2, assume there exists a unique integer an. Then the successor of, a sub the successor of n, that's kind of a mouthful to say, equals fn an will not be redefined by any successor of m, which is fm an, by axiom 2.4. And just to remind you what axiom 2.4 says, where was it? Over here. Different natural numbers must have different successors. All right. So here this gives you uniqueness. So we can define sequences recursively here with the natural numbers. Okay, so that's section 2.1. Like I said, there is a lot of more general and informal discussion that he talks about in the chapter, so you should read it yourself. This is the bare bones skeleton of the chapter, as I usually do when I do my summaries. So I highly recommend reading, what Terry Tao has to say in between these things, because I think it's really useful hearing his insight into stuff. All right, so let's go on to section 2.2. We'll do this one as well. And then once I finish this, I still haven't done the written up the exercises for 2.2. So I'll have to do that. And that's what I'll post in the next video. I'll post the solutions to the exercise sets for 2.2. Anyway, here's a summary though for section 2.2. Okay, we here in this section, we're going to look at addition of natural numbers, and to define addition, we'll use a recursive definition, which is written down here. So this is definition 2.2.1. Addition of natural numbers, let m be a natural number. To add 0 to m, we define 0 plus m to be equal to m. Now suppose inductively that we have defined how to add n to m. Then we can add n, the successor of n, to m by defining the successor of n plus m to be equal to the successor of n plus m. Right, so that's the recursive definition for addition, and we'll be able to use this to prove things about addition, which is what section 2.2 is about. All right, so here's a note. Using axioms 2.1, 2.2, 2.5, we can show that the sum of two natural numbers is again a natural number. He asks why. He doesn't actually state this as like a factor or anything. He just says this as like a note on the side, and he asks why. So I decided that I would prove it because this is the way that you're supposed to read math textbooks, right? When the author asks you, why do you think something is true? You should go and see why it's true. So here I proved that this statement is true using induction. So here's the proof that the sum of two natural numbers is again a natural number using the definition here, and the axioms 2.1, 2.2, and 2.5. Right, so here's the base step. 0 is a natural number by axiom 2.1, and then we go on to the inductive step. If we assume mn are natural numbers, such that n plus m is a natural number, then the successor of n is a natural number by axiom 2.2, and the successor of n plus m is a natural number by axiom 2.2. Therefore, the successor of n plus m is the successor of n plus m, which is a natural number. Right, so that proves that the sum of any two natural numbers is a natural number. Okay. Then he has a lemma for any natural number n plus 0 is n. Notice, even though this looks very similar to what we said up here in the definition, 0 plus m is m, notice here we're adding 0 on the left, whereas down here, in the lemma, we're adding 0 on the right, and we have not yet established that addition of natural numbers is commutative. So we can't assume commutativity of addition because we don't know that that's true yet. So we have to do this only using the stuff that we've already built up. All right, and we do it by induction. So here's the proof. If n equals 0, then obviously 0 plus 0 is 0 by definition. By definition, I mean of addition. Okay, so right, if you add 0 to 0 on the left, you get 0. If n plus 0 is equal to n, this is the inductive step, by the way. If n plus 0 is equal to n for some natural number n, then consider the successor of n plus 0. That's equal to n plus the successor of n plus 0, but by the inductive hypothesis, n plus 0 is n, so we just get the successor of n. And that shows that this property also holds for all natural numbers. Okay, next lemma, 2.2.3, for any natural numbers n and m, n plus the successor of m is equal to is equal to the successor of n plus m. Again, notice that while this looks very similar to what we established in the definition over here, it's not the same thing because, again, we were not able to appeal to commutativity of addition because that has not been established yet for the natural numbers. All right, so here we just have to use what we already know in order to do this. Okay, so again, this is done by induction. A lot of these proofs are done by induction because that's really all we have. Okay, so here we go. Let m be a natural number, then 0 plus the successor of m equals the successor of m by the definition that we had for addition. But that's the same thing as the successor of m plus 0 by the lemma that we proved a minute ago. Okay, so that shows that the base case is true. Right, then go on to the inductive hypothesis. The inductive step. Assume that n plus the successor of m is equal to the successor of n plus m for some natural numbers n and m. Then consider the successor of n plus the successor of m. Okay, that's equal to n plus the successor of m. Sorry, that's equal to the successor of n plus the successor of m. That's starting to become kind of a tongue twister there. And that is equal to the successor of n plus m by previously established things, and that is equal to the successor of m. I'm sorry, the successor of n plus m, and that proves that the property holds, right? So here we have that this is equal to this as well. Right, here's a corollary. For any natural number n, the successor of n is n plus 1. He doesn't actually prove this. He just says this follows by a corollary, and he does, he just says why. Why is that true? You should, look. So I proved it, but he doesn't prove this in the book. He just asks you why that is the case. So again, when you're reading through a math textbook, this is the way you should do it. So here's the proof. Let n be a natural number, then n plus m is equal to n plus the successor of 0 by definition. And that's equal to n plus 0. That's equal to the successor of n plus 0, which is equal to the successor of n, and that proves the statement. So the successor function, what it does is it adds 1 to the natural number n. And here I'm just showing where each of these equalities comes from. Right, this equality comes from limit 2.2.3, and this one comes from 2.2.2. All right, another proposition, 2.2.4, addition is commutative. Finally, we get to commutativity. So for any natural numbers n and m, n plus m is equal to m plus n. Right, and unsurprisingly, this is a proof by induction. So for the base step, n plus 0 is 0 plus n by lemma 2.2.2 in the definition of addition. Excuse me. Because both sides here are equal to n, right? Then the inductive step, step 2, let m be a fixed natural number. Assume for some natural number n that n plus m equals m plus n, and consider the successor of n plus m. That's equal to the successor of n plus m. We've already established that. And that's equal to the successor of m plus n by the inductive hypothesis, which is equal to m plus the successor of n by inductive hypothesis and lemma 2.2.3. So here we get that no matter what integer, if commutativity holds for some integer, sorry, I keep misspeaking. If commutativity holds for some natural number, then it also holds for the successor. Okay, so that shows that it holds for all natural numbers, n and m. Okay, here's another proposition. Past this point in section 2.2, a lot of these propositions are just stated, and the proofs of them are left for the exercises. So we'll get to those proofs when we do the exercises in the next video. All right, so proposition 2.2.5 says addition is associative, which the associative law means, for any natural numbers a, b, c, we have a plus b in parentheses plus c should be equal to a plus in parentheses b plus c. But he leaves that for an exercise for the reader to do as an exercise. So we'll do that, like I said, when we get to the videos on the exercise sets for 2.2. All right, we also have a cancellation law, which is sort of like a precursor to the operation of subtraction. There is no subtraction operation defined on the natural numbers, because you need the integers to make to make subtraction available to all the numbers. But here we have a cancellation law for the natural numbers anyway. So let a, b, c be natural numbers such that a plus b is a plus c. Then we have b equals c. So here's the proof. All right, so part one, the base step, b is equal to 0 plus b is equal to 0 plus c, which is equal to c. That's by the definition of addition, right? Which means that b equals c, so that holds for 0. Then we go on to the inductive step. Assume that a plus b is a plus c implies b equals c for some natural number a, and then we consider the successor of a. So the successor of a plus b equals the successor of a plus b, and a plus b is equal to a plus c by inductive hypothesis. Therefore, the successor of a plus b is the successor of a plus c, and that equals the successor of a plus c. Furthermore, the successor of a plus b is equal to a plus the successor of b, and the successor of a plus c is equal to a plus the successor of c, which implies that the successor of b is equal to the successor of c, which implies that b is equal to c by the inductive hypothesis and axiom 2.4. So that shows that addition of natural numbers has a cancellation law. Okay, definition next of what it means for a natural number to be positive. So a natural number n is said to be positive if and only if it is not equal to 0. If you don't include 0 in your set of natural numbers, then obviously you don't need this, but here we do. So we have a definition for what it means for a natural number to be positive. It just means it's not 0. Okay, here's proposition 2.2.8. If a is a positive natural number and b is a natural number, then a plus b is positive. Okay, so we prove this again using induction. So the base step says let a be a positive natural number, then a is not 0. Consider a plus 0, which is equal to a by one of the previous lemmas that we had. I forget which number it was, which is equal to a, but remember a is a positive number, so it's not 0, which means that the sum is positive. Okay, then moving on to the inductive step, let a b be natural numbers where a is not 0 and a plus b is not 0. Consider a plus the successor of b, that's equal to the successor of a plus b, which is not 0 by axiom 2.3. Right, that proves that if a is a positive natural number and b is a natural number, then a plus b is positive. Right. Next is a corollary. If a and b are natural numbers such that a plus b is 0, then a equals 0 and b equals 0. Now here, I did this with contraposition, whereas the book does it with contradiction. So my proof is completely different from his because, like I said, he uses a different proof technique. He uses the proof by contradiction, whereas I just used the contrapositive of the statement, and because that statement's easier to prove. However, if you don't know what the contrapositive is, you have to kind of know a little bit about elementary logic to do this stuff and proof techniques. But again, that stuff is in the appendix, and I'll do that on the appendix on the Patreon page. So, but assuming that you do know what a proof by contrapositive is, here I would assume, and actually I could do this without loss of generality because of symmetry in the hypothesis, or symmetry in the conclusion over here. Assume without loss of generality that a is not 0. So in other words, a is a positive natural number. Then a plus b is not positive. Sorry, it's not 0, meaning that it's positive. That follows directly from the proposition that we just did. And that just shows that the statement is true. So if a plus b is 0, then both a and b have to be 0. Right. And like I said, you can look in the book at how Tao does it. He does it with a proof by contradiction, but I did it this way instead. Okay, here's another lemma whose proof is left to the exercise set, but I'll read out the lemma anyway, and we'll do the proof, when we get to the exercises. So this is lemma 2.2.10. Let a be a positive number, then there exists exactly one natural number b such that the successor of b is equal to a. Right, we'll save the proof for that for the exercises. Okay, definition 2.2.11 next, which gives an ordering on the natural numbers. Let n and m be natural numbers. We say that n is greater than or equal to m, and we write using these two symbols here. This is read n is greater than or equal to m, or sometimes people read this. You can read this as n is greater than or equal to m, or sometimes people read it as m is less than or equal to n. And these two things mean n equals m plus a for some natural number a, right? So this symbol here, if you're not familiar, stands for if and only if. Whoops. I think my computer is loading. Hang on one second. Okay, if and only if. In logical terms, this is called a biconditional statement. Right. Definitions are always if and only if. Books usually don't write it that way. But anyway, we say that n is strictly greater than m and write n greater than m or m less than n if and only if n is greater than or equal to m and n is not equal to m. Right. So now we have an ordering by this definition on the natural numbers. Note that the successor of n is always greater than m implies that there's no greatest natural number, because if you assume that n is the largest natural number, then the successor of n is actually larger than that, so that doesn't make sense. So there's no largest natural number. All right, there's another proposition here whose proof is left for the exercises, but there's a lot of parts to this, so I'll read them out one by one, but we'll wait to prove it until we get to the exercises. Right, so these are just basic properties of order for natural numbers. Let a, b, and c be natural numbers, then here we have a bunch of properties. So part A, order is reflexive, which means that a is always greater than or equal to a for any natural number a. Part B, order is transitive, which says that if a is greater than or equal to b and b is greater than or equal to c, then that means that a is greater than or equal to c. Order is anti-symmetric, which means that if a is greater than or equal to b and b is greater than or equal to a, then a has to be equal to b. Property letter D, addition preserves order. If a is greater than or equal to b, a is greater than or equal to b if and only if a plus c is greater than or equal to b plus c. Property E, a less than b if and only if the successor of a is less than or equal to b. And lastly, property F, a less than b if and only if b is a plus d for some positive number d. And like I said, he leaves the proof of this for the reader to do in the exercise set, which we'll do in a separate video. All right, proposition 2.2.13. This is the trichotomy order for natural numbers. Let a and b be natural numbers, then exactly one of the following statements is true. A is less than b, a is equal to b, or a is greater than b. Now, he does give a proof sketch of this in the book. However, I decided, since the reason that it's a proof sketch in the book is because he uses certain facts that have not been proven, and he says the proofs of those statements will be left to the exercise. So I just think conceptually, to see this proof, it'll make more sense to just do prove the lemmas first by doing the exercise, and then I'll prove the statement myself after we have the lemmas. So even though he does have a proof sketch of this in the book, I'll hold off on proving it until after we do the exercise where we prove the lemmas that the proof depends on. All right, last thing here is the proposition 2.2.4, which is the strong principle of induction. Again, we've met the strong principle of mathematical induction in Spivak already, but here's a restatement of it. So let m0 be a natural number, and let p of m be a property pertaining to an arbitrary natural number m. Suppose that for each m greater than or equal to m0, we have the following implication. If p of m prime is true for all natural numbers, m0 less than or equal to m prime less than m, then p of m is also true. In particular, this means that p of m0 is true, since in this case, the hypothesis is vacuous. Then we can conclude that p of m is true for all natural numbers m greater than or equal to m0. Okay, and again, the proof is left for the exercise set, so we'll do that in a separate video. And that's the end of section 1, tech 2.1, 2.2. There is a section 2.3, which is on multiplication of natural numbers, which we'll do after we do the exercise set for section 2.2. All right, so I'm going to end the video here. Let me know what you guys think in the description below. Please do like and subscribe if you enjoy the content here. I do have the other stuff still coming up. I was just particularly motivated to do this because I've been reading this on the train, reading this book on the train recently. So, and if you want to take a look at the Patreon page, it's only $5 a month, which for that price, you get a bunch of extra content. You get lecture videos, you get homework assignments, you get solutions to the homework. So take a look at what we got going on over there. If you join, like I said, it's only $5 a month. You get a lot of stuff for it. In particular, I'll be adding the appendices to this book in on the Patreon page, right, which deal with logic and proof techniques. So we'll continue with this next time. I'll do the exercise set, and then the video after that will be section 2.3 and its exercise set. All right, I'll leave it here until the next video, guys. Keep learning, and I'll see you in the next one.